Welcome to a design video for the UWS-1 Ultralight airplane from the Ultralight Airplane Workshop. My name is Leon. This is a very exciting video because we're reaching another milestone for the design of the airplane. We're going to figure out the surface area for the horizontal tail. The first significant milestone we had in the design of the UWS-1 was figuring out the surface area for the main wing. And without that, we pretty much can't do anything else. The next major milestone is the one we're going to cover today, which is the surface area for the horizontal tail. And then the following milestone will be the surface area for the vertical tail. Now, the previous two videos that we did on the design for the UWS-1 covered the weight and CG, and the one following that covered the wing moment. We needed the information from those two videos before we could make this video. We needed the information from those videos to do the surface area calculations for our horizontal tail. Let's get into it. One of the things that's only semi-related to the surface area is the planform for the tail. One of the things I want to do is to have the airplane be at least somewhat aesthetically pleasing. And I thought, let's make the planform for the horizontal tail resemble the planform for the main wing. The main wing is a mostly elliptical wing with the tip cut off. And then also the sweep of the wing increases as you get out closer to the tip. Now the reason for that was to help make these trailing edges a little bit straighter, so I got to have a long flap here. And that also causes this main leading edge to trail back a little bit more than it would on an elliptical with a straight 25% chord. So I decided let's kind of reflect that on the horizontal tail also. And so that's what I've done. I've made it so that there's a little bit of a straight edge out here on the outer portion, and then this front portion has more of a curve as you get out to the tip. And that's really just for aesthetics. It really has nothing to do with the aerodynamics. But another portion of the planform does have to do with the aerodynamics. One of the guiding principles in designing the wings on an airplane is that the front airfoil should stall before a rear airfoil or any other aft airfoils on the airplane. And that's so that the airplane will pitch down, increase speed, and regain lift if that front airfoil stalls first. So this will be true for a conventional configuration like this ultralight we're working on, or even a canard configuration, or even a triple flying surface configuration. A canard in front, a main wing, and a horizontal tail. You want that front surface to stall first. One of the things that you can do to help ensure that the front flying surface stalls before the aft flying surface is to give that aft flying surface a small aspect ratio. And just a refresher on aspect ratio, it's essentially the span divided by the chord, but a more accurate way to determine it is the span squared divided by the surface area of the wing. Now this is a scan of a page out of Evans' Airplane Designer's Handbook, and it represents what happens to the slope of your coefficient of lift with respect to angle of attack as you change the aspect ratio. Now this line that's furthest out here represents aspect ratio of infinity. Of course, we can't build a wing that's infinitely long, but the next one is an aspect ratio of 8, and then 6, and this farthest one out is 4. So as you get lower and lower aspect ratio, you still have roughly the same maximum coefficient of lift, but it brings the slope further out so that your angle of attack at maximum coefficient lift gets farther and farther. So if you had a horizontal tail and a main wing that had the same exact airfoil, then if you have a lower aspect ratio out here on your tail, it should stall at a higher angle of attack than your main wing would, assuming it had a higher aspect ratio. And assuming just about everything else was equal also. So one of the things that we can do to help make that tail stall last, or the wing stall first, whichever way you want to think about it, is to use a low aspect ratio. So let's go back to the tail. So the aspect ratio on this tail is lower than aspect ratio of the wing. So that should help the wing stall before the tail does. Now let's figure out the surface area for a horizontal tail. What do we need to know in order to calculate that or determine it? Well, this equation here may look familiar to you from way back when we were working on the surface area for the wing. This S represents surface area. The W represents weight being carried by the wing. This Q is dynamic pressure, and we talked about that in the wing moment video. And of course, the C sub L is the coefficient of lift. What we need to do then is find out what weight the tail is going to be carrying, or another way to say the load that the tail is going to be carrying. Our dynamic pressure, so we need to know what speed we're going to be doing our calculations at. We'll assume that the atmospheric density is sea level. And then we need to figure out what coefficient of lift we want that tail operating at that speed and that load. Let's work on figuring out this load first. Figuring out the load on the tail is what the two preceding design videos were leading up to. That first one was calculating the position of the CG and the weight of the total airplane at CG. The second video was figuring out the pitching moment of the main wing. And this should look familiar to you because we used this same picture in those two design videos. And we talked about using this equation. Well, let's talk about these first two things again, just a brief summary, and I'm going to put a link up here in the right hand corner for the video where we talked about calculating the CG and the weight. And that's what this term in our equation represents. So this W is the total weight of the airplane, and this CG is the position of that weight relative to some reference. And if you remember, we decided to use our reference at 25% mean aerodynamic chord. And if you need a little refresher on what the mean aerodynamic chord is, I'll put a link up here in the corner. And in the next aerodynamic video we did, we talked about the moment of the wing. And that's what this curved arrow represents. It's the pitching moment of the wing due to the aerodynamic forces. And that's generally going to be pitching forward or down. And then the last portion of this equation is this LT and XT. This XT is the distance from the 25% mean aerodynamic chord of the wing to the 25% mean aerodynamic chord of the tail. And then this LT is the load on the tail, which is the W from our previous equation. Now this equation is telling us that when we are in a stable flight condition, you add all these terms up, and these are pitching terms, where the CG typically is trying to pitch down if it's in front of what the neutral point is, which we didn't draw here. And the wing pitching moment is trying to pitch down. And then the tail is trying to counteract that. And that's typical. It's not always true. So if we're in a static situation where we're not pitching up or pitching down, then when you sum all these components up, it should come to zero. Well, we know this term and we know this term. All we need to figure out are these two terms. Well, let's work on what this x sub t should be. There are really no hard and fast rules or simple calculations for determining how far back your horizontal tail should be compared to the wing. And just as a starting point, I decided to cheat a little bit, and I used an example of the Hummel Ultra Cruiser. And so I got out the plans and I did some calculations and figured out how far the horizontal tail mean aerodynamic chord 25% was for the wing mean aerodynamic chord 25% was. And what I came up with that was roughly 8 feet, about 97 inches. So that's what we're going to use for our XT. Now what we can do is change that if we need to. When we start to do our surface area calculation and we decide our surface area is too big for whatever reason it may be, maybe the tail won't fit in the trailer if it's too big, then what we can do is increase the x of t and move the tail farther back, and that'll end up letting us reduce the size of the tail. And the reason we can do that is a term called tail volume. If you take this x sub t and multiply it by your surface area, that's tail volume. And of course the reason it's volume is because you've got cubic feet from that multiplication term. Once you're happy with the static stability that you're going to get and the neutral point you're going to get from the surface area you've calculated for your tail, you can calculate that tail volume, and as long as you keep that constant, you can either change your x sub t or change your surface area. So if you make your x sub t larger, your surface area will come down by the same percentage. If you make your x sub t shorter, then your surface area will go up by the same percentage. So this is just a starting point. We can change it later if we need to. Let's go back to our pitching moment calculation then. we now know at least our initial attempt at x sub t, so we now have a value to use for that. Now we have to calculate what our lift is. And since that's the only unknown, all we have to do is pull this lift value over here, calculate what's left, and that gives us our lift value. And we can use a spreadsheet to help us do that. Let's think again about when we were doing those previous videos on the CG location and weight and on the wing moments. We ended up doing those at several different values. For example, we did it at several different weights. Those weights also moved, which gave us several different CG locations. We also had more than one moment value for the wing. Because we had several different speeds, we did some calculations at, and we did calculations with flaps and without flaps. Well, that means we're going to have several different lift values that we need to calculate. Let's do a quick review of the weights that we were talking about. The main thing that we were varying on our weight calculations was the weight of the pilot. We wanted to be able to have a maximum of a 250-pound pilot and a minimum of a 110-pound pilot. And then we were also going to pull a maximum of 3.8 Gs, and with the heavy pilot, that came out to be 2,082 pounds. So the total weight of the airplane maximum was 548, the minimum was 398 pounds. And we were moving the location of these pilots, which also moved our CG. Now for the wing moment, if you remember, we had different speeds we did some calculations at. We had a stall speed. We also have a cruise speed. We didn't do any calculations there yet, but we also had the maneuvering speed that we did some calculations at, and that maneuvering speed changes based on the weight of the airplane. And then we also had the situation where we had flaps deployed or not deployed. What I'm showing here is a little bit of a spreadsheet that I've used to do these calculations, and what we're doing now is figuring out the entire airplane moment, or actually using the airplane moment calculation, that one that sums up to 0 if the airplane is not changing in pitch. So here's the moment of the wing, and I pulled that down from another part of the spreadsheet, and we talked about that in the design video on the moment of the wing. You also have the moment due to the CG, and that's just the position of the CG multiplied by weight, and that's this row here. And then the tail length, what we just talked about, which is at 8 feet. Now we're doing these calculations for the moments at various conditions. So this first one is standard weight at landing configuration, which means flaps fully extended, and we're at the stall speed for the airplane. The next one is when we have a heavy pilot, but we're at stall with full flaps. And we're going to do a light pilot at stall with full flaps. And then we're going to go up to our maneuvering speed, and at that maneuvering speed we'll be pulling 3.8 Gs with the light pilot. We're also going to do with the light pilot when we're at our maximum coefficient of moment on that wing, but we are at our maneuvering speed. And then we're also going to do another one where we're at maximum coefficient of moment on the wing, but we're heavy pilot at our maneuvering speed. This collection of flight conditions should capture the larger moments that our tail has to counter. And one of those should be the condition that requires the largest surface for our horizontal tail. We should have the largest load on the tail at whatever our maximum summation of these two moments are. And that's what this line here is. We added this one and added this one, divided by the tail length, and that gives us the load on the tail, and that's in pounds. So if we run along here, we see that our largest load is 38 pounds down. So the tail's pushing down with 38 pounds. We have this very interesting condition here where the tail's actually trying to push up. And we talked about that back on the CG design video where we have a light pilot and that pushed our CG back much closer to our neutral point. And then we have these other conditions here. Our stall condition is pretty much the same for both our standard pilot and our heavy pilot. But that's because the wing moment dominates over the CG. There's almost no CG moment, but there's plenty of wing moment. and we have 35 pounds of downforce. Let's go back and figure out what we need to do to calculate our horizontal tail surface. So here's our calculation for the surface area. We need to load, and that's what we just finished figuring out. Need a dynamic pressure. That's going to change based on whatever speed we're operating at. And we need a coefficient of lift. Well, we know what speeds we are. We just talked about the various speeds that we're doing our calculations on for the wing moment. What is our coefficient of lift? I decided to kind of go the easy way out. Martin Hallman has a book called Modern Aircraft Design. In Volume 1, page 43, he talks about the coefficient of lift to use for your horizontal tail. And he says if you keep your maximum coefficient of lift you need for that tail to 0.8 or less, the wing should always stall before the horizontal tail does. So we're going to use our coefficient of lift of 0.8 for whatever our worst tail load is going to be. So went and did that calculation. So I grabbed Q from another part of the spreadsheet based on which speed we're talking about here. And then we're using the tail load and we're using our coefficient of lift of 0.8. And our wonderful little spreadsheet goes and gives us this calculation. So for the conditions we've looked at, the largest surface area we need is 22.5 square feet. Now you may remember our biggest tail load was out here at 38.4 pounds, but we only need a surface area of 2.5 square feet to deal with that. Well, remember, our speed is our maneuvering speed. That's up around somewhere in the low 70 knot range. Our stall speed, though, is at 24 knots. When you're increasing your speed, your flying surfaces become more effective by the square of the velocity. So this velocity here is way, way more than this. That means our Q is going to be much, much larger. If you remember our equation up here, a large number in our denominator is going to make this result smaller. That's what we're seeing here. That large Q is making our result smaller. Our worst case condition is at stall with our heavy pilot, and we need 22.5 square feet. Let's talk about calculating the neutral point for the airplane so we can figure out if it's going to be stable. Now, if you need a refresher on neutral point, I will put a link up here in the upper right hand corner, and you can go and review that to remember what the neutral point is and how we calculate it. But we now have two surfaces for our neutral point. We have the main wing and we have our horizontal tail. And I've got a little calculation here that shows the position of the 25% mean aerodynamic chord for both the wing and the tail, and the surface area. Now I'm not using 22.5 square feet. Right now I'm using 20 feet. That was my initial guess on what I would need based on the Hummel Ultra Cruiser tail area, and it turns out that's pretty darn close to what we calculated as 22.5. Now 20 will still work pretty well. That's only a 10% error. That means our coefficient of lift would change by 10% and be 0.9 instead of the 0.8 that we were looking for. And that's still within a margin of error of being safe. And I'll talk about that more when we do the airfoil selection for the horizontal tail. And we got our span of 27 for the wing, 7.5 for the tail. Now that span was based on wanting to be able to fit the tail into a trailer with an 8-foot wide opening at the back. So I've got the aspect ratio for each one. So remember we were talking about having a low aspect ratio for the horizontal tail compared to the main wing. So the main wing is roughly 8, horizontal tail is roughly 2.5, so that is definitely a low aspect ratio tail. Now if you remember again from the neutral point calculations, we need to know the width of the fuselage so we can do some correction factors for that. This is the slope of the coefficient lift versus angle of attack. Now it's based on the airfoil, and I'll get into that a little bit more in the next video, but the horizontal tail slope is a little bit higher than the wing. This lift slope number only takes into account the two-dimensional lift slope of the airfoil. It doesn't take into account the aspect ratio. That's taken care of in the calculation later. So those are all input numbers. The rest of these are calculations. And let's just get over to the exciting part. The neutral point for the entire airplane has been calculated to be 7.25 feet which turns out to be about 87 inches. And based on where the mean aerodynamic chord is, that neutral point is at roughly 36% of the mean aerodynamic chord. Now remember, we want to have our neutral point to be aft of the CG. Here are our CG calculations. With the standard pilot, we're at 25%. With the heavy pilot, we're still at roughly 25%. And with that light pilot, we're at 32%. So our neutral point is at 36. That means even with this farthest aft CG location, we're still 4% in front of our neutral point. So we should be statically stable. Well, I'm pretty darn happy with that first guess that we took at what the horizontal tail surface area was going to be based on what the Hummel Ultra Cruiser had. We are just a little bit less than what our calculations said we should be. Based on Ultra Cruiser, I had 20.2 square feet. Our calculations said 22.5 square feet. That's pretty good. In the airfoil selection video that we're going to do for the horizontal tail, I'll get into why having a slightly smaller surface area will be fine for a horizontal tail. We could even go smaller. I don't think we will, but we could. So that 0.9 coefficient of lift based on this surface area is going to work out pretty good for the horizontal tail. Like I said, the next thing to do on our design of the horizontal tail is to select an airfoil. And we'll also use that same airfoil for our vertical tail. And then once we get that done, we'll go ahead and get started on the vertical tail design. And we're going to do some of the very similar things we just did. We've got to figure out yawing moments instead of pitching moments this time that our vertical tail has to be able to take care of. Well, it's a relief to get to that milestone on the UWS-1 Ultralight airplane design. I'm looking forward to the next one, working on the vertical tail. Well, while this video is rendering and uploading to YouTube, I'll be working on my next video, which is a composite experiment video. In this one, I'm going to be working on an unusual flow media for carbon fiber infusion, and here's a little sneak peek of that. If you haven't already done so, and you'd like to see more of these design videos or carbon fiber infusion videos, make sure you subscribe to the channel. Hit that bell button and you'll get notified when new videos are uploaded. And while you're at it, if you haven't already done it, follow or like the Facebook page. There's a link down in the description. I sometimes post teaser photos there or little tidbits that I've learned that really don't warrant a whole video. So you can get a little extra information for that Facebook page. Well, I'm going to get back to it.